So let's take a look at the alkanes themselves. By definition, just the organic compounds that contain no functional groups themselves. It's only CH bonds and then CC single bonds. So if we have carbons with all single bonds, take a look at the structures of these alkanes here. All of the carbons are making 4 bonds, just like carbon normally would. So when carbon makes 4 single bonds, think of what its hybridization is. sp3. Add together one s and 3 p's, that makes 4 hybrid orbitals. So in alkanes, all the carbons are sp3 hybridized. Let's start at least our series of alkanes. We'll start with methane, the simplest of all the alkanes. So CH4, 1 carbon, 4 hydrogens attached to it. Methane is the main component of natural gas. So the stuff that powers our Bunsen burners that comes straight from our lab benches. If we add a carbon to it, we have ethane. We go from 4 hydrogens to 6 hydrogens. We don't go to 8 hydrogens because one of the hydrogens that was in methane gets replaced with the carbon. So there's a CC bond now on each of those carbons, so the 3 remaining valences have hydrogens to them. Add a carbon, we get propane, C3H8. Add a carbon to that, we get butane, C4H10. What I'd like you to notice about each of the structures of each of these is that, let's start over here in butane. Each of these carbons has, in their structures that are drawn out here, they have a hydrogen up and a hydrogen down, one above and one below the carbon, plus there are 2 hydrogens on the ends. So hydrogen on the left side, a hydrogen on the right side. That'll always be the case on any string of carbons. There'll be 2 hydrogens per carbon plus 1 on each end. So we can use that idea to make a general formula about how many hydrogens any alkane will have. So if an alkane has N carbons, how many hydrogens does it have? Well, it at least has twice as many. So if I have 4 in butane, we see at least that there's 1 going up and down on each of those carbons, so there's at least twice as many, plus there'll always be 2 extras because of those 2 on the ends. So putting that in a formula, if N is our variable, number of hydrogens is 2N plus 2. That's specific for alkanes, though, where we have only CC single bonds. And specifically if there are no rings either. We'll get to cycloalkanes later because that changes our formula a little bit. But if it's just an open chain like that, twice as many hydrogens plus 2 extras for the end caps. A way of classifying alkanes is to say that they are saturated with hydrogens, meaning of all the places where hydrogens could possibly be bonded, the molecule is filled up with hydrogens. So all of carbon's available valences are filled with hydrogens. There is no way that we could get any more hydrogens into this molecule, in other words. Sometimes those are also called aliphatic, Aliphatic compounds. So the ones we showed above are called straight chain alkanes. Sometimes they're also called normal alkanes, where the carbons are connected to no more than 2 other carbons. So end carbons are just attached to 1. Any carbons in the center of these chains are attached to one to the left and 1 to the right. So those are the straight chain alkanes. Specifically, you can tell a carbon is straight chain by going from 1 carbon all the way to the other end carbon without picking up your pencil and without retracing your path. So a lot of students are confused a little bit. I can have one that turns corners, goes to left and right and up and all over the place, but that's still a straight chain alkane because I can go from 1 end carbon to the other by tracing through all of the carbons in between and never picking up my pencil, never retracing my path. That is a straight chain alkane, or an N alkane. We said normal up here. We'll use that abbreviation N in front of a name to mean normal. So if we start with butane, anything butane or longer can be branched. It can have 1 or more carbons that connect to 3 or 4 others. So a branched alkane, a simple branched alkane, might look like this one, where I have 3 carbons in a row, but another carbon attached to the center. And we can do this pencil test. If I start on one end, I can go through 3, but I can't get to that 4th one unless I retrace my path. So no matter how I go, no matter where I start, I can't get to all the carbons unless I pick up my pencil or if I retrace my path. That's the simplest test. So that might be something you'll have to do a little bit, but it should be very, very quick when you can realize that a chain of alkanes is either straight chain or branched that way. So let's talk a bit about what constitutional isomers are. They're just molecules that differ in how their atoms are connected, but they have to have the same molecular formula, and that just means they have all the same atoms, but they're just connected in a different order. Okay. So if you're making a model kit, you'd have to unplug an atom from one place and plug it in somewhere to a different atom in order to get a constitutional isomer. And then you'd have a molecule that's fundamentally different from the one that you started with. So take a look at butane and isobutane. Isomer that we get by just forming one branch, like from butane to isobutane, will usually have that iso prefix. So on small, simple molecules where we've only made one branch, a lot of times that iso prefix can be made. So the way I would get from butane to isobutane would be to unplug one of these carbons on the N and swap it with one of the hydrogens here on a different carbon. So we go from having a straight chain alkane, where I have 1, 2, 3, 4, to a branched alkane, where I have only 3 in the longest branch, plus 1 that's attached beside it. So as you get to larger molecules, there are more constitutional isomers. If we start with normal pentane, so just 5 carbons in a chain, I could make one branch compound by removing one from the end and swapping it with a hydrogen, so making one branch. But then I could make another branch by picking another one off the end and attaching it again to that same compound. So 2,2-dimethylpropane, which we'll have a common name for it. We'll have a different name for it in a little bit, but it's a compound that actually has 3 carbons in its longest chain plus 2 carbons branched off of the middle one there. So generally, the larger a molecule gets, the more possibilities there are for constitutional isomers. That's just sort of a statistical reality of it. So with our alkanes, the way we get constitutional isomers is by changing the carbon skeleton, so changing the way that the carbons are actually attached to each other. So that's like butane and isobutane. As soon as we introduce functional groups in, we can make constitutional isomers by having different functional groups that are made out of those same atoms. So, for instance, an OH on the end of a molecule is an alcohol, right? 2 carbons with an OH, that's ethanol. I can instead put that oxygen in between the 2 carbons, and now I end up with an ether. In both cases, there's the same molecular formula, C2H6O, but depending on which functional group we have, we'll have 2 very different molecules. Similarly, you can take the same functional group and attach it in different places. So in one of these cases, here's an NH2, an amino group attached to carbon 2 of a 3-carbon chain. In another case, here's the amino group attached to carbon 1. So being able to attach them to different places will make different molecules, and those molecules will have similar properties because they're the same functional groups, but they will be slightly different, especially in terms of boiling point or something like that. So let's show you a couple different ways that we draw alkanes. Different methods are handier in different circumstances. Just the molecular formula of something like butane, C4H10, has no structural information. We have no way of telling the way that the atoms are attached when all we say is C4H10. It could be any of the possible constitutional isomers that make up that substance. It is possible to draw structures out showing all the bonds, although we typically only do this at sort of the start of first semester organic chemistry, when we're still familiarizing ourselves with how it is that hydrogen bonds and how many bonds it's making and so on. It's very tedious to do. We only do it when it's absolutely necessary, and very soon in here we're going to be moving beyond drawing out all the C's and the H's. But if I really wanted to, I could draw 4 carbons all in a row. 1, 2, 3, 4. I could put 3 hydrogens on each of the N carbons. I can put 2 hydrogens on each of the 2 middle carbons. There we have the straight chain, the normal butane. Butane has a constitutional isomer where we've got 3 carbons in a row, 1 carbon attached to the central carbon. Each of those end carbons are CH3s. We're going to see that the end carbon is always a CH3, right? If carbon only makes one other bond, it has to have the remaining ones as hydrogens. Then don't forget this 1 hydrogen on the center carbon now, so that everything gets 4 bonds. So that's fine. That's useful to us, I suppose, if we absolutely need to see where all the atoms are. But it's not going to be tremendously useful to us in the range of the course as we're doing it. It's going to be just sort of a time waster. So that's where condensed structures, again, they can still show how all the atoms are connected, but we don't draw any bonds. So I guess the simplest condensed structure for that straight chain 4-carbon alkane would be just writing CH3, CH2, CH2, CH3. So just start with the carbons and then say how many hydrogens are attached to them. And there's all kinds of variations on this. Sometimes the carbon-carbon bonds are drawn. So we could do CH3, align CH2, line, CH2, line, CH3, line. That means the exact same thing. We can combine adjacent groups. So CH3, CH2, parentheses 2, CH3. Or you can combine identical groups that are attached to a common atom. That's common too. So the way I could draw a very simple condensed structure for the isomer of butane, isobutane up there, because there are 3 CH3 groups attached to that central carbon. So I could say CH3, parentheses 3, CH. So that only works if groups are repeated and directly connected, so one after another, or if you have identical groups that are all attached to the same carbon. So these 3 ones I have here are the straight chain. I've drawn the isomer right here in this one. So condensed structures are useful to us. Line structures are very handy. We've drawn these before. Just make carbon chains a zigzag. 1, 2, 3, 4. Up, down, up. For that isomer, I'll go up, down, and then one going straight up on the center carbon. You can make very complicated branched alkanes using line structures without too much trouble at all. So we'll be making a lot of good use of those line structures. One thing though, just to be careful of with single bonds, remember single bonds can rotate around each other. So whenever there's that sp3 hybridization, there's going to be rotation. So don't fool yourself into thinking that by turning corners, you're making anything different than what you had originally. So if I just draw carbon skeleton here, that carbon skeleton where I went over, down, over, and up is just the same as having 1, 2, 3, 4, 5 carbons all in a row. So please don't fool yourself with that. That's one of the dangers of drawing out all of the bonds on something, because things that are the same actually end up looking a lot different depending on which direction you've drawn them. Much less likely to have that in a condensed structure, even less so in a line structure when you're just making zigzags. So let's name these straight chain N-alkanes. The names for the compounds with 1 through 4 carbons are historical names, which means those names came up with before anybody knew what actually they were made of. So they have names that, mean other things, and you can do some searches, go look in Wikipedia or something, and you'll see the whole history behind all of those if that's interesting to you. But 5 and beyond are named based on the number of carbons. So methane, ethane, propane, and butane, those are the 4 historical names for 1 through 4. It turns out those starts of the names, meth, eth, prop, and bute, will be used all throughout organic chemistry to represent 1, 2, 3, and 4 carbons. So meth, eth, prop, bute. The end of the name, just like always, tells us what kind of compound it is. So sort of a prefix and a suffix So the prefix in these names will often indicate how many carbons there are. The suffix, the end of the name, will tell us what kind of molecule it is. Pretty simple. 5 through 10, pentane, hexane, heptane, octane, nonane, and decane. Those just come from Greek prefixes, meaning the respective numbers 5, 6, 7, 8, 9, and 10. You should recognize some of these. Octane, you hear about with the octane rating on gasoline. There's a nice section in the end of your chapter that explains in pretty good detail where that octane number comes from. So I suggest you read that if that's interesting to you. You need to memorize the names for these compounds 1 through 10 if you haven't already in previous chemistry class. But look these over, make sure you can memorize these because, as I said, the names of many other organic compounds will be based off of these simpler alkanes. There's a way to systematically name straight chain alkanes like this that are hundreds of carbons long. So be thankful that we only have to learn up through 10. Undecane and dodecane are 11, 12, and so on. Icosane and triacantane, I guess, are 20 and 30, but those are really very rare to see anymore. So 1 through 10, though, very important for us to learn. There are also going to be some common names for some isomers, which we need to be familiar with. So, like I mentioned before, when we have iso at the beginning of a name, that usually means we've just made one branch. So isobutane still has 4 carbons, but we'll now have one branch. So we'll do CH3, CH, CH3, and then a new CH3 on that second carbon. So that's isobutane. Isopentane has 5 carbons and 1 branch. Only one way to do that. CH3, CH2, CH, CH3, but again with a CH3 attached to either of those central carbons. Remember I said there's only one way to do this with one branch. If I made that branch sooner, that would have been this same thing, but just flipped over. So still just one molecule. Neopentane has 5 carbons, but now 2 branches. So the way I'll draw neopentane over here, I'll draw just a C in the center, and then 4 CH3s coming off of it. So we call this neopentane because there's 2 branches. It's not iso where there's just one. When there's 2 branches, we can say that there's a 3-carbon chain going straight through the middle here. On the middle carbon, there's one going up, and then there's one going down. And that's it. So isobutane, isopentane, and neopentane are names for common isomers that you should be aware of.